optimizing multi-scale representations to detect effect heterogeneity using Earth observation and computer vision. Applications to 2 anti-poverty RCTs. Abstract. Earth observation EO data are increasingly used in policy analysis by enabling granular estimation of conditional average treatment effects, CATE. However, a challenge in EO-based causal inference is determining the scale of the input satellite imagery, balancing the trade-off between capturing fine-grained individual heterogeneity in smaller images and broader, contextual information in larger ones. This paper introduces multi-scale representation concatenation, a set of composable procedures that transform arbitrary single-scale EO-based CATE estimation algorithms into multi-scale ones. We benchmark the performance of multi-scale representation concatenation on a CATE estimation pipeline that combines vision transformer VT models, which encode images, with Causal Forests CFS to obtain CATE estimates. From those encodings, we first perform simulation studies where the causal mechanism is known, showing that our multi-scale approach captures information relevant to effect heterogeneity that single-scale VT models fail to capture as measured by R². We then apply the multi-scale method to 2 randomized controlled trials RCTs conducted in Peru and Uganda using Landsat satellite imagery. As we do not have access to ground truth CATEs in the RCT analysis, the rank average treatment effect ratio rate ratio measure is employed to assess performance. Results indicate that multi-scale representation concatenation improves the performance of deep learning models in EO-based CATE estimation without the complexity of designing new multi-scale architectures for a specific use case. The application of multi-scale representation concatenation could have meaningful policy benefits, e.g., potentially increasing the impact of poverty alleviation programs without additional resource expenditure. Earth observation EO data play an increasingly important role in policy analysis by providing researchers with contextual information to estimate treatment effects at a more granular level, revealing characteristics of environmental conditions, land use patterns, economic development, and climate variables. Anderson et al., 2017, Daoud et al., 2023, Burke et al., 2021b, Peterson et al., 2023, Kino et al. A growing body of work therefore focuses on estimating household or neighborhood-specific conditional average treatment effects. Kate Sakamoto et al., 2024, Jerzak et al., 2023, Serdava, 2023, Giannarakis et al. 2023, Go et al. 2022, 2023. An important application of EO-based policy analysis lies in anti-poverty randomized controlled trials RCTs, where the outcome Y is the household income for the unit that the satellite imagery is centered on, and the treatment W is cash transfer to the household. The researcher's goal is to estimate effects conditioned on available satellite imagery M. We denote this estimate for a given image, tau hat applied to M. In order to do so, we encode M into a sufficiently low-dimensional representation phi that preserves maximal information about Z, the set of unobserved background features that are relevant to treatment, e.g. the village geography, baseline wealth. See the white nodes of Figure 2 for illustration. A key characteristic of EO-based images in the context of effect heterogeneity estimation is the inherent multi-scale nature of the relevant background features Z for observational units, a phenomenon termed multi-scale dynamics. Figure 1 provides some intuition for such multi-scale dynamics in EO-based inference, where information relevant to heterogeneity is encoded in both the local area around a household and the broader neighborhood around which the household is situated. Figure 1, the Washington Longfellow National Historic Site left, with context, right. Using sentences in the RSICD dataset, clips nearest neighbor text embedding to the images are, the square with some halls and lawns is in a rectangular region which SIC is in the middle of the forest, and here is a zone of apartment buildings between a river and a road respectively, showing that the model extracts separate, novel information from the 2 images. Along with Figure 1, we provide a visualization in Figure 2 that provides a more formal illustration of our setting. Parts highlighted in blue refer to multi-scaled components of the DAG that were previously not considered in effect heterogeneity estimation methodologies. Our contribution is to propose multi-scale representation concatenation, a procedure that transforms single-scale EO-based CATE estimation algorithms into multi-scale ones by concatenating the image representation tensors. We benchmark using a single-scale CATE estimation algorithm previously used in anti-poverty RCTs, Jerzak et al., 2023. A remote sensing fine-tuned image model, CLIP RSICD, is used to generate lower dimensional representations of single-scaled satellite imagery, Liu et al., 2017, Arut Union et al., 2021, Radford et al., 2021. A causal forest CF model then produces the final CATE estimates. Beyond building on top of previous work in causal inference, there is a rich body of work investigating multi-scale phenomena in computer vision, which we have drawn inspiration from to develop multi-scale representation concatenation. We survey them in section 8.4. Figure 2, a DAG showing the relationship between the various components involved in CATE estimation. The I subscript is the observation unit index, the subscript SS1 or S2 is the scale of the variable. The blue components are the components of the figure that reflect multi-scale dynamics. Multi-scale representation concatenation allows algorithms that previously were only a function of m sub i's for a single s to utilize both m sub i's 1 and m sub i's 2. Note that this diagram could be extended to additional scales. Image resolution is assumed fixed. To quantify performance in real randomized controlled trials RCTs lacking ground truth CATE data, we use a measure of the degree of effect heterogeneity detected by a model, rank average treatment effect ratio rate ratio, as our metric. We find evidence that applying multi-scale representation concatenation improves the rate ratio, and, thus, potentially improves accuracy of CATE estimates and policy targeting. As extensions, simulation studies are used to validate results from the RCT analysis due to the difficulty in evaluating model performance on RCT data, where ground truth CATE is unknown. Section 4, a scaling analysis demonstrates that multi-scale representation concatenation can significantly boost the performance of CATE estimation models in EO-based causal inference beyond just 2 scales. Section 5.3, and an analysis where we assume the CATE analyst has limited prior information on the geographic distribution of household units finds that multi-scale inference improves the rate metric under this weaker assumption. Section 5.22. These suggest promising further areas of exploration. Background and contributions. An enduring question in EO-based causal inference is how to best estimate tau of m, which is defined as the expectation of y sub I of 1 minus y sub I of 0 given m sub I equals m, i.e., the CATE for pre-treatment image array, m sub I. In theory, one would provide all available covariates to an oracle function generating estimated tauums to obtain the most accurate causal estimates. For EO-based causal inference, this would ideally involve using the largest, highest resolution satellite image available. However, in practice, this function is difficult to estimate due to the high dimensionality of m sub I. In this context, because there are well-understood methods to estimate CATEs from WY and pre-treatment covariate vectors, a natural approach in image-based CATE estimation would be to introduce an encodify that maps high-dimensional imagery into a lower-dimensional representation. However, in an EO-based causal inference context, a pre-trained image encoder may struggle to capture both household-specific and neighborhood-level contextual information. In some cases, adding additional contextual information can even degrade performance if the model fails to distinguish relevant from non-relevant signals. Model fine-tuning could address this issue, yet it remains difficult due to the small size of most RCTs. Our main contribution, therefore, is to develop multi-scale representation concatenation, a family of procedures that transform any previous single-scale procedure into a multi-scale 1 through tensor concatenation. It is especially suitable in data-constrained settings, for example, RCTs, as it requires minimal additional data requirements. The strong interpretability of the procedure also makes it simple to explain to relevant stakeholders. Further, it requires limited model experimentation. The optimal concatenation procedure can be found by systematically varying the image size and combining image representations from different scales. Multi-scale representation concatenation thus transforms the problem of designing architectures specific to the multi-scale dynamics of the problem at hand to a less complex inference time computational search. We examine the improvements in model performance when incorporating multi-scale representation concatenation in the context of randomized controlled trials conducted in Peru and Uganda. Methodology. Let I index the experimental units in the study. Each I has a geolocation denoted by x sub I in R superscript 2, representing spatial coordinates, for example latitude and longitude, and a binary treatment indicator W sub I encoding whether the unit received treatment. The observed outcome from the RCT for unit I is y sub I in R. Let y sub I of 1 and y sub I of 0 denote potential outcomes under treatment and control. Identification will be performed assuming unconfoundedness and SUTVA. Now define an image fetcher that generates an image from a coordinate x sub I in R superscript 2 with a specified size s in n sub plus. This fetcher is denoted f sub capital I applied to x sub I s, producing an element of script m in symbols m sub I, s equals f sub capital I applied to x sub I, s, and m sub I, s is. In script m here, m sub I, s is the image of size s greater than 0 centered at x sub I. Size refers to the width of the raw satellite imagery in terms of pixel number, with pixel resolution fixed. Next, because of the high dimensionality of m sub I, s, we need to introduce a causal representation extraction function phi, which maps script m superscript c to r superscript d. This function phi takes c in n sub plus images as input and outputs a d-dimensional feature vector. The projection of the image to a lower dimensionality makes estimation tractable in finite samples. We develop a multi-scale representation concatenation procedure that constructs phi from base image encoders, denoted f prime sub phi sub sk, mapping script m to r superscript d prime, to easily adapt single-scale representation extraction functions into a multi-scale setting. Although our algorithm is generalizable to arbitrary c, for concreteness, our exposition will be limited to the case where c equals 2, with f sub phi mapping script m times r superscript 2 to r superscript parentheses 2 times d prime n parentheses. Concretely, phi sub I, s1, s2 equals f sub phi applied to m sub I, s1, m sub I, s2, which equals the ordered pair, parentheses f prime, sub phi sub s1 applied to m sub I, s1, f prime sub phi sub s2 applied to m sub I, s2 end parentheses, where s1 and s2 are two different image sizes. In this paper, f sub phi is constructed through representation concatenation of the outputs of base image encoders f prime sub phi sub sk, along with, optionally, a dimensionality reduction function r, so that f sub phi applied to m sub I is 1, m sub I, s2, is equal to r applied to the pair f prime sub phi s1 applied to m sub I is 1, f prime sub phi, s2 applied to m sub I is 2. Here, r to the power 2d prime goes to r to the power l less than 2d prime. Given SUTVA and unconfoundedness, with w sub I being the binary treatment indicator for unit 1, the CATE given representation phi sub i's 1, s2 is defined as tau of phi sub I s1 s2 equal to e of y sub I of 1 minus y sub I of 0 or phi sub I s1 s2 SUTVA equal to e of y sub I or phi sub I s1 s2 w sub I equal to 1 minus e of y sub I or phi sub I s1 s2 w sub I equal to 0, unconfoundedness 1. Given phi sub i's 1s 2 and unconfoundedness, CATE can be estimated using a function h sub theta, r to the power 2, d prime goes to r, hat tau sub I equal to h sub theta applied to phi sub i's 1s 2, where hat tau sub I is the estimated CATE for unit I based on the extracted features. To estimate CATEs, we need to estimate both the representation extraction function phi and the estimation function h sub theta. Our goal is to learn a function f sub phi that extracts the most causally relevant covariates from the image at multiple levels of representation, e.g., household and village. Having found f sub phi, we then draw upon the CF approach, a well-established method for estimating tau under unconfoundedness. With this algorithm for estimating CATEs, we then seek to maximize the heterogeneity signal of different multi-scale representations using a metric, mu of dot, designed to quantify the extent of effect heterogeneity detected given input features. In our case, mu of dot will denote the rate ratio as a principled metric that allows one to evaluate model performance without ground truth individual treatment effects, overcoming the unobservability of true CATE values. For a set of image conditioning variables m sub y, the rate is rate equal to integral from 0 to 1 of alpha of q times E of y sub I of 1 minus y sub I of 0, or f of tau of m sub I greater than equal to 1 minus q minus e of y sub I of 1 minus y sub I of 0, dq. 8 among top QTH percentile under rule, tau baseline 8. A more detailed exposition is in section 8.3. The rate ratio, the measure μ, is defined as rate divided by the standard deviation of rate. Motivation for using the rate ratio lies in the fact that 1, it is interpretable and comparable across contexts as a scale-free quantification of heterogeneity signal, and 2, it can be used as an asymptotic t-statistic of the existence of treatment heterogeneity in the population given the conditioning data, here, pre-treatment satellite image arrays. The detailed algorithm for rate ratio estimation is presented in section 8.3. The rate ratio is chosen as the primary metric for model evaluation due to its comparability across RCTs and outcomes. However, rate ratio is not as interpretable as the more policy-oriented metrics of rate and Gini curves. Rate alone is a summary measure of heterogeneity in the data captured by the model and downstream policy relevance of the current heterogeneity model. And Gini curves plot the gain over randomization of assigning treatment according to CATE estimates from a model. We validate the rate ratio metric with the values produced by these two alternatives. We find a high correlation between the three metrics, indicating that in our context rate ratio also quantifies the policy benefits of a specific CATE estimation model. Due to the high correlation, we leave rate and Gini figures for the appendix, Figure 12, Figure 13, Figure 14. For a discussion of Gini curves, see section 8.5. With this way of generating representations from images, CATEs from representations, and heterogeneity measures from CATEs, we now formalize our optimization when performing multi-scale inference. Our optimization proceeds by comparing a multi-scale heterogeneity signal against a baseline of comparison involving the optimal single-scale only input. Specifically, we have the following optimization goal: max sub S1, S2. The expected value of μh applied to theta f, applied to phi f, applied to phi m sub I, s sub 1, m sub I, s sub 2. Max sub s, the expected value of μh applied to theta f, applied to phi sub m sub is. Expectations are taken over population variability. The resulting optimized value is g, the multi-scale gain. While optimization over S1 and S2 does not depend on s, we include the term involving s to establish a baseline. If g is negative, we have evidence in favor of using single-scale only representations. We use grid search for optimization. See 8.7. Simulation. While the rate ratio is a useful theoretical metric, contextual scale evaluation in an applied context is difficult due to the lack of ground truth CATE data. In developing our methods, we thus use a simulation to supplement findings from the later RCT analysis. Our simulation employs images of size 3232 and 256 pixels drawn from the Peru RCT. We design 3 image perturbations corresponding to 3 scales of causal features. See Figure 3. We perturb images' household-level features by masking the center of the image, neighborhood-level features by adding an image fading to the edge of the larger scale image, and global context features by applying image contrast. For each of our experiments, we choose a subset of these perturbations, each applied independently to half of the data. The different experiments help us discern how our model will perform when differentially scaled signal with Gaussian noise. See Figure 3. In our simulation, we design a setup that mimics an RCT. Each unit has an associated image, and we apply various perturbations, such as masking or edge fading, to these images. The specific type of perturbation applied to a unit's image determines its outcome and associated CATE. We systematically test the ability of different modeling strategies to detect and leverage these image-based signals in estimation. We measure how well we identify features driving the outcome of interest with the 5-fold cross-validated out-of-sample R-squared. The distribution of y sub I is defined as y sub I is distributed according to n, with mean equal to 0, and VR equal to 2 if I is not perturbed, is distributed according to n, with mean equal to 100, and variance equal to 100 squared if I is masked, is distributed according to n, with mean equal to 100, and variance equal to 100 squared if I is edge faded, is distributed according to n, with mean equal to 100, and variance equal to 100 squared if I is contrasted, is distributed according to n with mean equal to 0 and variance equal to 200 squared if I is masked and edge faded. Figure 3. Visualization of image perturbations right and their corresponding distributions left. The equation defines the distribution of y sub y based on the perturbations applied, while the images illustrate these perturbations for different image sizes. Masking used in the simulation experiment is 2 by 2 pixels, enlarged here for visibility. With the outcome and image data defined, we then train a multi-layer perceptron MLP on top of representations generated by the CLIP model to predict the outcome of the units. We defer further details to the appendix. For a single-scale approach, the input to the MLP is the representation generated by the CLIP image encoder of an image of a fixed size. We then apply multi-scale representation concatenation with no dimensionality reduction to generate the multi-scale analog. 3 sets of experiments are performed on the perturbed dataset to explore performance of a multi-scale modeling approach when A, only household or neighborhood level information is present in the dataset, B, when both levels of information are present in the dataset, and C, when the global feature is present in the dataset. We found that our simple concatenation-based multi-scale modeling can recover most of the information present on one level of resolution and capture signals simultaneously from both scales if present. Perhaps more surprisingly, multi-scale modeling also better captures global features. Figure 4. Experiments 1A and 1 billion apply household neighborhood-specific perturbation. Experiment 2 applies household and neighborhood-specific perturbation. Experiment 3 applies global perturbation that has a uniform effect on the whole image. Experiment 1 shows that even if there are no cross-scale effects, multi-scale concatenated procedure can recover much of the signal at one scale. Experiment 2 validates that the procedure can capture multi-level signals if present and outperform a single-scale approach. Experiment 3 suggests that multi-scale representation concatenation could improve a model's ability to capture predictive signals even when the signal is recoverable from any one scale. While the investigations present here isolate the influence of specific local, intermediate, and global perturbations, we investigate all possible combinations in the appendix. Where an additional global perturbation of 90-degree image rotation is included, the results accord with those presented in Figure 4, application to anti-poverty RCTs. While the simulation results are suggestive of potential benefits of multi-scale analysis, we now turn to quantify its benefits in the context of real RCTs. Our analysis here draws on unique experimental datasets from diverse country contexts, Peru and Uganda. For both, there is evidence that SUTFA is satisfied, as spillover effects are determined to be unlikely, and treatment implementation is standardized. These datasets therefore provide a solid foundation for exploring the impacts of scale across different societal settings. Data, treatment, imagery, and outcome. The Peru data are drawn from a program designed to alleviate poverty, with treatment occurring from 2007-2014. The outcome is household poverty. Treatment is a multifaceted intervention that combines short-term aid and long-term support. Due to image availability, we use Landsat 5 satellite imagery between 2000 to 2003, with 30 minutes pixels centered around each household, applying a cloud mask and median filter over images. Visualized in the appendix. Figure 10. The Uganda RCT was also designed to reduce poverty here, by giving young people business grants to improve human capital. Treatment occurs from 2008-2012, and data are drawn from the Landsat 7 ETM Plus mosaics from 2000s for their high quality and image resolution, 14.5 meters pixels. For Peru, geolocations at the household level are available, whilst for Uganda geolocations are only available at the village level. Because the Peru geolocations are at the household level, we can analyze the average pairwise image overlap of individuals in the same village. The analysis shows an increase in percentage overlap with image size, left panel of Figure 5. We further find that image representation distance decreases as the image size increases, right panel, emphasizing the need to use large and small images to obtain heterogeneous representations between individuals inside the same village. Figure 5, left. Average pairwise overlap of input images for individuals in a Peru village when image width is varied. Right. For CLIP RSICD, the mean Euclidean distance of representations inside the same village decreases with increasing image width. Multi-scale RCT analysis. We next conduct multi-scale RCT analysis on the two datasets using the CLIP RSICD image model. Results from the Swin and Clay model are reported in the appendix. We concatenate CLIP household image representations from images of widths 16, 32, 64, 128, 256, 349, i.e. 0 meters, and use a CF as CATE estimator. Rate ratio is used as our evaluation metric, with results for rate and Gini curves in the appendix. Due to the composability of our multi-scale procedure, different base image encoders can be chosen for images at different scales. For simplicity, we use the same base encoder throughout. Overall, we find that multi-scale representation concatenation improves or does no worse than single-scale only analyses. Using a suitable dimensionality reduction function, R further increases the performance of a multi-scale procedure. Improvement over single-scale baseline. We first analyze the improvement of the multi-scale procedure over the baseline via equation 3, where we subtract the optimal single-scale from the optimal multi-scale rate ratio to quantify the relative increase in heterogeneity signal. The multi-scale gain metric is reported in Table 1. With benchmark CLIP RSICD-based analysis, strong evidence for multi-scale heterogeneity is found in Uganda G equal to 0.95, E equal to 0.10, and 0.4, 1 Z equal to 0.09 for PC and raw representations respectively. Some evidence is found in Peru equal to 0.68, equal to 0.09, and 0 is equal to 0.08 for PC and raw representations respectively. Table 1, rate ratio differences from equation 3. Standard errors in parentheses. CLIP RSCCD, an EO fine-tune of CLIP. PC denotes principal component representations. S star, S1, S2 denote optimal image dimensions in the single and multi-scale cases using raw uncompressed representations. Table 1 also provides insight into the optimal image dimensions selected in each data model analysis combination. Strikingly, although the largest image context, 349 pixels, is the best for single-scale Uganda analysis, when compared with the multi-scale concatenated procedures, in no case is the largest image context best, i.e., using the largest image array does not maximize the heterogeneity signal in either of the RCTs. Moreover, smaller images generally generate higher heterogeneity signals than larger images. This hints at some of the challenges in multi-scale analysis, where features from larger images are packed into a fixed dimension embedding space, leading to the possible degradation of information related to important household or village-level dynamics. Analysis of RCT results. With further analysis, we find more evidence for the use of multi-scale information by the heterogeneity model. In Figure 6, we see that the optimal rate ratio occurs when we concatenate representations from a large image with those from a more localized context. This difference is larger in Uganda than in Peru, in terms of raw pixel numbers, but may be partially explained by the higher resolution of the Uganda images. Because multi-scale representation concatenation increases the dimensionality of the input covariates to the CATE estimation model, dimensionality reduction techniques could improve model performance. Figure 7 displays the rate ratio heat maps from PC compressions of the neural features 50 dimensions. Using PC representations, we see even stronger evidence for the role of multi-scale representations in improving heterogeneity signal and stronger model performance, as evaluated by the rate ratios. And the optimality point is shifted towards the center of the heat map. We did not do an exhaustive search for the optimal PC procedure, but anticipate that the performance of multi-scale would improve further with further optimization of the dimensionality reduction technique employed. Evidence of multi-scale use by heterogeneity model. Due to the interpretability of the concatenation-based multi-scale procedure, we can directly investigate whether is evidence that the heterogeneity models are incorporating information from multiple scales in forming effect estimates. We probe the utilization of multi-scale information in Figure 11. Here, we find that the effect heterogeneity model, in general, uses information from both scales in modeling treatment effects. Figure 6, analysis of rate ratios for Uganda and Peru RCTs across a range of S sub 1, S sub 2 values. Higher lighter values are better. we see that the maximum heterogeneity signal in both RCTs is detected with small medium-sized S sub 1 approximately 64 and large S sub 2 approximately 350. Star indicates optimal selection. See Figure 12 for analysis using rate values instead of ratios. Figure 7. Analysis of rate ratios across a range of S sub 1, S sub 2 values with PC representations. Higher, lighter values are better. Star indicates optimal selection. We measure the CF model's information utilization by examining the fraction of the top 10 most informative features via CF derived from representations at the smaller scale, i.e. phi sub I, S sub 1. Values near 0.5 indicate balanced use of smaller and larger scales. Values near 1 indicate dominance of unit scale features. Those near 0 indicate dominance of larger scale ones. According to this measure, gain from multi-scale information is stronger in Uganda imagery than in Peru imagery, a finding congruent with the analysis of rate ratios. A confounding factor here could be the lower resolution of the Peru imagery, which decreases the amount of information detectable with smaller scales. Multi-scale dynamics with weak prior information about unit locations. Although we observe an improvement in rate ratio in using multi-scale representation concatenation, the procedure so far described requires strong prior information on the geographic location of households. We therefore investigate performance when we randomly sample image centers so that they are no longer centered around villages' households. To investigate this, we displace household and village locations so that small images no longer contain information from the target unit's location, and rerun the same analysis as above. We find that there is a decrease in multi-scale dynamics for raw representations for Uganda weak prior information G of 0.19 and Z equal to 0.08, for Peru a difference of SE, but not for PC representations, for Uganda a G of SE, for Peru, SE, and for PC and raw representations respectively. More broadly, Figure 8 shows that, even with only weak information about unit locations, multi-scale analysis can improve signals about heterogeneity. Scale information is not specific to household-level features, but also other features about localized contexts. We also find that heterogeneity signals are actually higher when using displaced images than the actual images around units, mean rate ratio of 2.24 versus 2.13, averaging across all method and data choices. In other words, even without household-specific knowledge, heterogeneity signals can still propagate through the integration of multi-scale features into effect heterogeneity modeling. We investigated this in further simulations and found that multi-scale analysis improves signals about heterogeneity, although less than the case with strong prior information. See Table 3 in the appendix. Figure 8 shows analysis of rate ratios for Uganda and Peru with displaced image centers across a range of S sub 1, S sub 2 values. Higher lighter values are better. Star indicates optimal selection. 5.3. Scaling scales. We next consider whether any scaling regularities emerge as the number of concatenated scales grows. Figure 9 investigates dynamics related to the number of scales employed. The average rate ratio increases with the number of concatenated scales, indicating that incorporating information from multiple scales enhances the model's ability to detect treatment effect heterogeneity. The rate ratio rises from approximately 2% for a single scale to a peak of around 2.5% when 5 scales are concatenated. Beyond this point, performance stabilizes, as evidenced by the rate ratio remaining at 2.5% for 6 scales. This suggests that concatenating up to 5 scales captures increasingly diverse information related to household-specific features and broader contextual dynamics to improve the heterogeneity signal, though additional scales beyond this threshold yield diminishing returns due to potential redundancy. This pattern is consistent across Peru and Uganda RCTs. Figure 9, as the number of scales grows, so too does average rate ratio performance. The dotted gray line marks 1.96, which represents the 5% significance threshold for detecting heterogeneity, assuming asymptotic normality. Overall, we see that multi-scale representation concatenation improves the performance of deep learning models in EO-based CATE estimation, whether information is strong or weak about the exact location of observational units. Moreover, multi-scale representation concatenation is interpretable in that investigators can readily probe the relative performance of different multi-scale choices on heterogeneity signal, noting that, in comparison, Many of the multi-scale inference strategies described in the computer vision literature up to this point are, to a point, black box, and do not offer a ready interpretation of which scales matter and which do not. Multi-scale representation concatenation thus introduces a composable procedure that allows any single-scale procedure to integrate heterogeneity information from small and large images to better capture both individual heterogeneity and neighborhood-level effects, allowing for more informative causal inferences. Discussion. Larger images are not always better. A counterintuitive finding from our analyses is that using the largest possible satellite image context, 349 pixels, never maximizes the heterogeneity signal in any of our experimental conditions. This challenges the intuitive assumption that incorporating more contextual information necessarily improves causal inference. We find this bigger is not better principle manifests in three ways. First, in single-scale analyses with unperturbed geolocations, smaller images often generate elevated heterogeneity signals, likely because they better capture household-specific characteristics without dilution from broader contexts. Second, even in multi-scale analyses, the optimal combinations typically pair a small or medium-sized image around 64 pixels with a large but not maximum-sized image, rather than using the largest available scale. Third, multi-scale analysis can provide for robust inferences even when only approximate location information is available, as evidenced by the displaced locations analysis. These findings have implications for EO-based causal inference. Rather than defaulting to the largest possible image context, researchers should carefully consider the trade-off between capturing relevant local heterogeneity and broader contextual information, either employing multi-scale representation concatenation or incorporating multi-scale dynamics into the inferential procedure in other ways to be robust to the intricacies of EO data. Towards adaptive multi-scale representation concatenation, despite grid search's promising performance, its computational requirement is exponential in C, the number of scales considered for combined analysis. Further, the current multi-scale representation concatenation technique limits itself to a fixed image scale combination for each observational unit, whilst in practice the optimal scale for each observational unit may differ. Our finding that multi-scale representation concatenation outperforms single-scale analysis suggests that there may be a way to optimize multi-scale representation concatenation further by estimating an additional function L from M to R squared that takes in a large image over an entire region around an experimental unit and outputs locations X sub I, where an image at each scale is centered. This would involve evaluating each geographic location for suitability of analysis, where dense prediction techniques could prove helpful. We present the estimation of L as an open problem. Multi-scale dynamics beyond EO. Multi-scale dynamics are present in diverse geospatial, biological, and public health contexts. Beyond CATE estimation, these dynamics are relevant for environmental cost-benefit analysis, EO-based poverty imputation, and confounder control, where the latent geospatial confounding structure may operate with multi-scale dynamics. We invite further work to incorporate multi-scale dynamics in these diverse settings. 7. Limitations and conclusion. This paper addressed the methodological challenge of capturing multi-scale dynamics in EO-based causal inference. By combining representations across scales, our approach captures both fine-grained individual-level details and broader contextual information, enhancing the estimation of CATEs. Simulation studies and analysis of two RCTs demonstrate the promise of multi-scale inference in outperforming single-scale-only methods when effect heterogeneity information exists at multiple levels. This offers a promising solution to finding a trade-off between individual heterogeneity and neighborhood-level context, and contributes to the growing literature on deep learning for causal inference. Limitations remain. First, the approach here assumes sutva and unconfoundedness for identification, and thus, an extension to observational inference requires additional assumptions. Second, images used in our study have low resolution, and resolution likely interacts with the gain from doing multi-scale analysis. Third, using high-resolution images in a multi-scale approach raises privacy concerns. Fourth, the approach taken to assess the validity of multi-scale representation concatenation is empirical. Theoretical results would strengthen our understanding of the method. Fifth, the approach is currently only validated on anti-poverty RCT datasets. Further research could be done to address these limitations of the general multi-scale representation concatenation approach.